Thank you. So I have many connections with many talks here. And I'm going to be talking about mostly pricing limits, infinite structures that way. So a quick reminder of the finite and infinite Ramsey theorems. Finite Ramsey theorem is about coloring finite sets inside of a finite set and finding a large enough finite set where you can get monochromatic color. And then the infinite Ramsey theorem is about coloring, say, M-size subsets of the natural numbers into finitely many colors, and then finding an infinite subset where all of your M-size subsets have the same color. So you can already think of Ramsey's theorems as structural because you can think of them as being on complete graphs or complete hypergraphs, and think of them as edge colorings and then looking for a monochromatic complete subgraph. All right, so now we move into finite structural Ramsey theory in earnest. So for structures A and B, we'll write A less or equal B if and only if A embeds into B. And we'll write B choose A to denote the set of copies of A inside of B. And these days, some people are coloring embeddings rather than copies, but there's a correspondence between them because you just multiply by the number of embeddings. Okay, so a class script K of finite structures, think finite sets, finite graphs, is going to have the Ramsey property if whenever you're given a structure A that embeds into a structure B, then, and you're given a number of colors, you can find a structure C in your class that's large enough so that for every coloring of your copies of A inside of C into your number of colors, you may find a copy B prime of B inside of C, where your copies of A inside of B prime are the same color. And so a lot of work has been done over the decades on Ramsey property and finite structures, beginning with Natasha and Rado for ordered free amalgamation classes, and then a recent culmination of much of strong amalgamation, not fully, but very close, by Hubitschka and Natasha in their 2019 paper that appears in Advances. And so so I believe that Rihanna has given you a very good tutorial this week on Friese structures and classes. And so you probably have way more examples than these to think about. But if you get lost, you can always think about the class of finite linear orders, the class of finite ordered graphs, the class of finite ordered Capelet-free graphs. These all have the Ramsey property. So now the question, at least that I like, is which infinite structures carry analogs of the infinite Ramsey theorem? So now we're trying to fix an infinite structure, fix a finite substructure, color your copies of that finite structure inside of your infinite structure in the finitely many colors. Can you get a copy of your infinite structure with one color? Or if not, can you bound the number of colors? Yes, and you already know the answer to this. So we'll get there. Oops, I went backwards. All right, so let's look at the rationals as a case study. So the rationals have the pigeonhole principle, which means that if you color the rationals into finitely many colors, you can find one color class which contains a dense linear order as a suborder. Okay, so a copy of the rationals as a linearly ordered structure. So you see the rationals have a pigeonhole principle, but if you try to even color pairs of rationals, you will already fail to get an analog of the infinite Ramsey theorem. So this idea goes all the way back to Sierpinski, 1930s. Where his actual paper was coloring sets of real numbers, but his arguments work for rationals too. And his key idea is to enumerate the rationals in order type omega, right? And if you do anything with infinite structures or sets, and Ramsey property, this idea of Sierpinski is laced through everything. Okay, so he decided to enumerate the rationals and then play the rational order against the enumeration order. So we'll color a pair, Qi, Qj, where I is less than j as an index. Red if Qi is less than Qj as a rational. And then blue if Qj is less than Qi as a rational. Okay, and so we get these two colors. And so imagine this is our copy of the rationals. It's nice dense linear order. We've enumerated 0 to be Q0, say, and -1/2 to be Q1, etc. And the Sierpinski coloring gives you that this pair is red because 1's less than 6 and -1/2 is less than 3/4. Right, but this pair would be blue because 0 is less than 7, but -1's less than 0. Okay, and no matter what you do to find a sub-dense linear order of the rationals, both of these patterns are going to persist. So we call this an unavoidable pattern or an unavoidable coloring. Okay, so jumping to because I'm going to go, I want to cover a lot today in 15 minutes. So jumping to Ramsey theory of the rationals, Devlin culminated all of the work on this in his thesis at Dartmouth with Baumgartner. And he showed that if you fix an M, and you color all of the M-sized subsets of the rationals into finitely many colors, you can always get down to this number, C sub 2m minus 1 times 2m minus 1 factorial colors inside a copy of the rationals. Okay, and so if M is 1, your bound is 1, that means you have the pigeonhole principle. We get a monochromatic subcopy if you're coloring rationals. If you're coloring pairs of rationals, Sierpinski's coloring is as bad as it gets. And any other coloring can be cut down to 2 colors, but not only just 2 colors, you can cut down to the coloring given by Sierpinski. So one color where the rational and the omega ordering line up and another color where they disagree. Okay, so now more generally, think of K as a Freisler limit, but it also could just be a universal structure or some class of finite structures. We define a Big Ramsey degree with this phrase was coined in Heckers, Hudstock, and Djordjevic in 2005. We call it K, we say that K has finite Big Ramsey degrees if given any finite substructure A of K, there is a number bound T, so that whenever you color your copies of A inside of K into R colors, you can find a copy K prime of K. So infinite substructure of K isomorphic to K, where you have no more than T colors. Okay. And then the Big Ramsey degree of A in K is denoted T of A if it exists. And these pop up a lot, right? So we saw the Sierpinski coloring on the rationals, and moreover, in general, for a Freisler structure, if it's not rigid, if there's more than one automorphism of it, then there will be a finite structure where you cannot get an analog of Ramsey's infinite theorem. But I should point out that even if there is more than one automorphism of K, it's very often that you still do get a pigeonhole principle, right? So like vertex colorings often still do get down to one color in a subcopy of your structure. But when you look at sets with size 2 or greater, then it's going to go up. So this is just a little side note, okay, so not little, but you know, side note for today. Part of the last 2 decades worth of finite structural Ramsey theory has been motivated by this KPT correspondence between the Ramsey property for a Freycinet class and extreme amenability of the automorphism group of its Freycinet limit. Okay, so although finite structural Ramsey theory progressed over the decades very well, it's had a recent surge in the last 2 decades. And in their paper, they have, you know, if you look at their chapter 9 of their paper, 11 of their paper, they have a slew of questions. One of which was try to find a correspondence of that sort, but at the level of Big Ramsey degrees. And Andy Zucker has done one direction of it, and he's working on the other direction. And there are good things happening there. Okay, so for Big Ramsey degrees, if that's all you care about, you could just work in a universal structure. You don't have to actually work in the Freycinet structure, but for reasons that hopefully will become clear a little bit later, I've been very interested in working in the Freycinet structures themselves. So a structure K is homogeneous if it's the Freycinet limit of a Freycinet class, right? And what that means is that if you have any isomorphism between 2 finite substructures of K, you can extend that to an automorphism of all of K. Okay, and then it's universal for a class of, say, finite structure script K if every member of script K embeds into big K. So Freycinet limits are universal for the Freycinet class, and they're also homogeneous. And 3 key examples that we'll talk about today are the rationals, the Rado graph, and the Triangle-free Henson graph. And one of the reasons that Freycinet limits are good for Ramsey theory is because you have the extension property, you have an infinite pool of potential vertices with which to extend a given finite structure to a copy of your next slightly bigger finite structure. And so you have the infinite pool with which you can cut down with a pigeonhole principle to a smaller number of colors. Okay, so Big Ramsey degrees over the years, they progressed quite much more slowly than finite structural Ramsey theory, mostly because of lack of methods. Okay, so this result of Devlin that I mentioned already had at its core a combinatorial theorem due to Millikan, which builds on the Halpern-Loikley theorem, which Whaley talked about yesterday. So I'll give a little drawing of that in a second. This Laflamme-Sauer-Vuksanovich theorem showed that the Rado graph has finite Big Ramsey degrees and also characterized them, also using the Millikan theorem for upper bounds. Okay, and then this result developed a level colored Millikan theorem to deal with this structure, which is the rationals with an equivalence relation with n many equivalence classes, each of which are dense inside the rationals. So Millikan extension, Millikan. Okay, so what is Millikan's theorem? So Millikan's theorem is the Ramsey theorem for strong trees. And its application is to get upper bounds for Big Ramsey degrees of unrestricted. So unrestricted includes rationals, Rado Graph, Homogeneous, digraph, things like that. Product Theorem has been successfully used for hypergraphs, right? So free amalgamation classes or things that are very close to Q that don't have forbidden substructures is the deal, right? And so what Millikan's theorem does is, I mean, I'm drawing it for 2, but it can be finitely branching infinite tree. And what you do is that you encode a universal structure into 2 to the less than omega or k to the less than omega as the nodes in some tree. And you find a coloring, right? You're given a coloring. And what you can do is, given a coloring, you can envelop it inside of a strong subtree, which would look essentially something like this. And then you're coloring all of your copies of this strong tree. You're applying Millikan theorem. You're getting 1 color per structure type. And that gets you the upper bounds. Okay. And I want to point out also that Halpern likely is pigeonhole or Millikan. So it's built on the Halpern likely graph. So this is how these 3 big examples, the rationals, the Rado graph, and these Q sub n's, and the dense linear order were found. Right, but what we didn't have then were methods for things with forbidden substructures. So in order to figure that out, I had to invent some new methods, coding trees, forcing, and get a new sort of Millikan style theorem applicable to Henson graphs. Okay. I'll go through some of those a little bit later. And then the exact Big Ramsey degrees were pretty close to what I did in the original paper. And then independently, Balko, Hodansky, Hubitschka, Konieczny, Vena, and Zucker got the same result around the same time. So then we started collaborating. And so then these are more results that have followed using these methods of coding trees and forcing, and I will go through a little bit of that in some further slides. Okay, so main points, all Henson graphs, so all k-click-free random graphs were done. Upper bounds, and then exact big degrees here. Big Ramsey degrees for structures which behave similarly to unrestricted structures in a way. And then some infinite dimensional results, which I'll get to a little bit later. And then there's been a whole bunch of recent developments not using forcing. So there's been category theory, there's been product Millikan, there's been Ramsey theory for parameter words, which you may have heard of in the reverse math world, as the first non-forcing proof for the Henson graph, and some more stuff. So these upward bounds done by Hubitschka paved the way for getting the exact Big Ramsey degrees for the homogeneous partial order with a linear extension. And then we use Laver's product Millikan theorem has been used for infinite languages and a whole bunch of other stuff going on. So Big Ramsey degrees have become big, and there's quite a lot to look at from the computability theory point of view. There's a lot to look at from the reverse mathematics point of view, and I'll get into a little bit of that towards the end of the talk with some current work with Peter and Charlie. Boy. Okay, so but let's look before that at characterizations of Big Ramsey degrees. So Big Ramsey degrees are characterized via basically 4 bits of information. The first bit is what you get by doing Sierpinski's enumeration of your structure in order type omega. So because we can, we do. So you assume that your universe of your structure is omega, okay? That induces a coding tree of 1 types. That coding tree of 1 types was implicit in prior work using Millikan's theorem at the end of the day when they got the exact degrees. Diagonal antichains are a means of sort of thinning out how quickly your substructure changes with regards to your original structure. Oops, passing types are what encode your actual structure. And then if we have free amalgamation with some forbidden substructures, there's other things that you have to take care of. So the first ingredient is enumerating the universe. So we'll let the universe of our structure K be omega. And that will induce a coding tree of 1 types, which, although it was sort of had some predecessors in other papers, it was first put forth as a concrete definition in this paper. So if you fix your structure K in order type omega and you start looking at the finite initial bits of it, that will induce this model theoretic idea of looking at your quantifier tree complete 1 types over the first n vertices of your structure. And then let's keep track of which member of your tree is supposed to encode your nth vertex. Okay, and then the tree ordering is just inclusion. So here's a coding tree of 1 types for the rationals, which is a retrospective of what Devlin did, getting rid of a lot of the noise that he had to deal with coming from this perspective. So if this is our first rational, we denote it by some coding node. Well, you could be either right or left of Q0. Q1 is to the right of Q0, so we denote it here. And now you can either go to the right or the left of Q1. If you're already to the left of Q0, you're definitely to the left of Q1, so that node doesn't have to split. Right, and so this is how you build a coding tree of 1 types for the rationals. And so forth. Okay. And so this approach actually really streamlines a lot of Devlin's work. And this approach is in the paper with Colson and Patel. And what we get, the second ingredient, is actually quite quick from that approach. A diagonal anti-chain means it's an anti-chain where your coding nodes are encoding your substructure. This is a subtree of the previous tree, okay? And the coding nodes are terminal, so they're making the anti-chain. And then diagonal means that you've thinned through so much. So each level of your tree, right, is corresponding to some original bit of your enumeration of the rationals. And you're saying, we're going to make differing decisions with respect to our original enumeration as slowly as possible, basically in pairs, right? So each level of this diagonal structure or diagonal anti-chain has at most one splitting into two nodes at each level. And this is seen in a whole host of different structures. So we can look at Dublin's coloring inside of the rationals from this perspective. And this is a red coloring of pairs. And this is another red coloring of pairs. And then this is a blue coloring of pairs. And another blue coloring of pairs. And the Ramsey theory of the structures viewed through the trees tells you really that you have a Ramsey theorem for each diary or type encoding a pair, right? This is one type where the left one's higher than the right one, and the other type where the right one's higher than the left one. And you get one color per type. So it's like you're enriching your structure, utilizing your enumeration of order type omega, and saying, okay, we actually do have a Ramsey theorem for our enriched structure, right? And so part of what is the problem with Big Ramsey degrees is finding out what is your optimal enriched structure so that you do get a Ramsey theorem for that. Okay, and the third ingredient for the Rado graph and other structures which are more complex than the rationals is something called passing types. So here is a coding tree for the Rado graph. And here's the graph enumerated in order type omega. And we're going to just say that going right means you have an edge and going left means you don't have an edge. And so if you go up to C4, you see it has to have an edge with C3, no edge with C2, no edge with one edge with C0. And that completely codes this edge between B4 and B0. And nothing else. Okay, so coding tree of one types for the Rado graph. You also get these diagonal anti-chains. But the difference between this and the rationals is that the right-left numbering in the tree tells you about the edge-non-edge relation. Okay, so Laflamme, Sauer, and Vuksanovich got an exact characterization of the Rado graph and things which behave similarly to the Rado graph, we're calling unrestricted structures, in terms of these diagonal anti-chains infinitely k to the omega, where k is twice the number of binary relations that you have. And then in this paper, we extended a bunch of previous results and got some new results by using coding trees of one types and forcing to get a pigeonhole principle, which is acting like Halpern-Whiteley, so that you can build a Millikan-style theorem for these coding trees. And we got indivisibility for structures with this amalgamation plus property for any arities, and then exactly Ramsey degrees, which behave like the rationals or the Rado graph for structures with arity at most 2. Okay, so here's Big Ramsey degrees in the Rado graph. This is the diagonal anti-chain. If you take your diagonal anti-chain well enough, you will code Rado Graph. Okay, this is the passing number edge, which means that these two blue nodes code an edge. Yellow is also passing with an edge, so those two yellow nodes code an edge, and then these two pink nodes code a non-edge inside of here. Okay, so these are, yeah. Nothing structurally. So they're the same, they're gonna, I probably shouldn't have colored them. I should have colored this yellow and that yellow. Yeah. Okay. Then upper bounds for binary pre-amalgamation classes as a total are found by Andy Zucker, also using coding trees and forcing. So a pre-amalgamation class is something exactly of the form forbidden F, where F is some set of finite irreducible structures. So that means that any two vertices in an irreducible structure are lying inside of some relation. So think like clique, or if you had two edges, you might have like a triangle with two edges in one type and another edge in another type, or you might have like a three-area relation, and you might have tetrahedron. Okay, if you're irreducible, you can be forbidden, and we still have finite Degrees for those. Okay, and then building on those upper bounds, we were able to characterize the Big Ramsey degrees of the free amalgamation classes using diagonal antichains. And then the next 4 bits of information are what are keeping track of how initial bits of your forbidden substructures are growing inside of your subtree with respect to the original enumeration. So I'll give a picture of this for the triangle-free graphs pretty soon here. So for triangle-free graphs, this is what the diary, or the, well, let's call it the diary. Diagonal antichain encoding a triangle-free Henson graph, which has the extra information that you need. So these are just telling you, the yellow bits are telling you edge, non-edge. The blue bit is something that starts to show up when you have forbidden substructures. So here we have forbidden triangles. So what is a triangle? Inside the tree, it's a vertex, 2 edges with the same vertex, and then an edge with something in another, right? So they start to pop up by these 2 blue edge relations at the same level. And so you keep track of, you thin out, and you make pairs of new edges with a common vertex in your original structure, happen just in pairs, thin them out. And then the other thing is the controlled coding level, which is essentially saying our structure after that coding node is going to be as small as possible, but still having the ability to extend it to a triangle-free Henson graph. Okay. So in the triangle-free Henson graph, these are the diaries for edges and non-edges. So the Big Ramsey degree for edges is still 2, just like in the Rado graph. But unlike in the Rado graph, the Big Ramsey degrees for non-edges is now 5. And it happens because there are just so many more ways to code a non-edge with this additional information popping up. Right. So one thing that's very different about the triangle-free graph versus the Rado graph is that every sub-tree coding the triangle-free graph must retain the leftmost path, with no edges. Whereas in the Rado graph, you can take any old subtree pretty much and still code the Rado graph inside of it. So that gives us more information to play with. Okay, so now a little bit about infinite dimensional Ramsey theory on omega and then on structures, because this is some of the newest work I've been working on, and so I'm most excited about it. I also put it in the abstract, so I should probably talk about it. Okay, so we're going to say that a subset of the Baire space is Ramsey if for every infinite set M of natural numbers, you can find a smaller set N, which is again infinite, so that either your infinite subsets of N are contained in X or disjoint from X. So what is this? This is a coloring of the points of the Baire space. So it's a coloring of infinite sets, right? And you can say being in X is colored 1, being out of X is colored 0, and a set X is going to be called Ramsey if you can cut down to some infinite subcube where X has a pigeonhole principle. Okay, so back to Ramsey's original theorem. In topological form, we can state it this way. For any M and R, if X is a union of basic closed sets, just neighborhoods where the neighborhood is dictated by an initial segment of size, the same size M, then your set is Ramsey. Okay, and this is the Ramsey theory, topological Ramsey space theory notation for just the neighborhood set, which starts with the set S and then end extends into omega. Okay, problem is that there are sets which are not Ramsey if you extend the axiom of choice, which I often do. So yeah. So the solution, which was suggested by Dana Scott back in the late 60s, was to restrict to definable subsets. So that there was a slew of work in the late 60s, early 70s, showing closed sets are Ramsey, Borel sets are Ramsey, analytic sets are Ramsey, and then the culmination with this Ellentag theorem saying that property of Baire in a refined topology is completely characterizing Ramsey sets and something called completely Ramsey, which is on another slide. Okay. So here's the Ellentag topology. It's a refinement of the metric topology on the Baire space. And we'll say that a set is completely Ramsey if it has the star property. So now we have a pigeonhole principle where you want to keep the finite bit of your basic open set in this refined topology, but you're allowed to shrink the infinite tail. So it's like Matthias forcing with that. And Ellentag, building on work of Galvin Perkery, was able to show that the property of Baire with respect to this Ellentag topology exactly characterizes the sets with this completely Ramsey property. And so this Ellentag space is the prototype, yes?
Sorry, is A any infinite set?
A is any infinite set, small set of omega, yes.
Thank you.
Yeah, thank you. So this Ellentag space is the prototype for something called topological Ramsey spaces, which were first looked at or sort of consolidated by Carlson and Simpson to find a common theme between a bunch of other infinite structural or word Ramsey theorems. And the idea is that your points are infinite sequences of some finite structures or sets, and their topology looks just like that. And then your topological Ramsey space, if and only if every subset with the property of Baire, is completely Ramsey with respect to that topology. Okay, so another one of these problem 11s, section 11 of KPT, was to find infinite dimensional Ramsey theory for structures, for Bryce structures. So a constraint was the Big Ramsey Degrees, right? So more work had to be done on that first before getting to this. But something that was a little bit funny was that although the coding node enforcing mechanisms were developed to take care of triangle-free graphs, they actually helped with this problem even for the Rado graph. So here's a snapshot of current work on infinite dimensional structural Ramsey theory. So these are all done using coding nodes and forcing. The forcing is to basically get you a Millikan style theorem for the coding trees. Okay. So in particular, for the free amalgamation classes, we can make infinite dimensional Ramsey theorems, which exactly recover the Big Ramsey degrees. And to do that, you really do need to work with these coding trees because you really want to encode your homogeneous structure, not just a universal structure, in order to get this recovery. And for people who like topological Ramsey spaces, one of the nice things that came out of our work was that we were able to reduce the strength of one of the axioms into, I failed to mention that. So Carlson and Simpson started this topological Ramsey space consolidation, and then Sidorchevich has his 2010 book, which is one of my staples, where he makes a collection of axioms, 4 axioms, which guarantee you a topological Ramsey source or Ramsey space. And so we were able to show that one of these axioms was overkill. You don't actually need it. Okay, so here's the triangle-free Henson graph again. And so what do we mean by infinite dimensional Ramsey theory on these sorts of spaces? We mean you've fixed a diagonal antichain that's encoding your structure. And what you're coloring now is subcopies of this with all the bells and whistles. And you must restrict to 1 because Big Ramsey Degrees dictated. If you don't, you will not get any infinite dimensional Ramsey theory. But we're saying that if you do fix any nice enough diagonal antichain encoding your structure, you can get, right, here's like 0, 1, 2, right? It's like inside of the bare space collection of infinite substructures where we're getting topological Ramsey spaces. Okay, so finally, probably this was not in my abstract, but probably the most exciting thing to talk about here. So computability theory results. Right, so I made a little problem list back in 2018 and I threw down the gauntlet and some people took it up and came up with this AMS memoirs, which is coming out very soon. And so it's, 150 something pages. There's way more theorems than 3 in there, but I'm just quoting some of these, their theorems, which are related to things I've talked about already. And so the rationals in the Rado graph, you can do the Big Ramsey Degree theorems in ACA naught. And there's a computable coloring of pairs of rationals. All of these subcopies had 1 color. A minimal number of colors, that's going to definitely compute the halting set. But then the Rado graph has conavoidance. Moving to triangle-free Henson graph, upper bound was able to be shown. Their upper bound is based on Hubitschka's work with parameter words. And I think that if you go another route, you might be able to get this down further. But using they showed exactly what the upper bounds, at least for that parameter, were Ramsey space theorem, and then applied it to get this. And then in some current and ongoing work with Peter and Charlie, we have shown that there is a computable coloring for pairs of non-edges in the Henson graph, so that if you take any subcopy of the Henson graph with the minimal number of colors, you're going to compute zero jump. And then more generally, if you have any n greater or equal to 3, there's going to be a graph which is n click free, and a computable coloring of its copies inside of the Henson graph, so that any copy with the minimal number of Big Ramsey degrees is going to compute 0 to the n minus 2 jump. So I don't know if this picture is going to make sense to you, but hopefully it will. So here's the coding tree for the triangle-free graph. So over here we have a triangle-free graph. It's enumerated in order to omega. There's its coding tree. When you're looking for these coloring theorems to get you some strength, you're looking at where you're going to get the lower bounds inside some diagonal antichain. So this is some diagonal antichain encoding a subcopy of the Henson graph, but it can be really wild, right? It doesn't have to be a tree. It's not going to be a tree. You don't know exactly which of these levels is going to extend infinitely much, but you do know that some of them will. And so using those ideas, we can show that you can code a Jackish coloring inside of there for non-edges, so that you get zero jump in any subcopy with the minimal number of colors. And H4, so this is the 4-click-free Henson graph. You can see it has a lot more branching than the triangle-free, but still not full branching. And some similar ideas can be used for that. So that is my overview of Big Ramsey degrees on some of the many tri-say structures which are out there, and some connections with infinite dimensional Ramsey theory and some connections with computability theory, reverse math. And I should mention that the infinite dimensional Ramsey theory is also very interesting for reverse math. There are a couple papers with Linda Rustrick and Reed and Demir and some other people, but still largely unexplored. So, if you're interested in a forcing proof of the Halpern-Likely theorem, I would recommend this one because it's the least typos. It has typos, plus you can't get it on MathSciNet for some reason. But it's the original Harrington forcing proof of Halpern-Likely as outlined to be by Rich Laver. This one is earlier, but actually more complicated because they wanted to reduce the large cardinal. They wanted to reduce the uncountable cardinal used in the application of Erdős-Fano and the forcing proof. So if you're interested in smaller upper bounds for not the degrees, but in terms of the strength of what you actually use in the theorem, this. If you don't care, use this. So that is it. Well, thanks.